Sweet. Wonderful. Sweet. Good to go. Okay, well, thanks, Kasha, for the intro. Excited to be here with y'all to chat about additive manufacturing for high-volume manufacturing of electronic devices. So, like Kasha said, I'm Kris Erickson. I'm a materials research manager at Meta. So I lead a materials group that is researching next-gen XR devices. All right, so lots to cover within the talk. Gonna outline some topics, define a few spaces, additively manufactured electronics, as well as heterogeneous integration. I'll reference these throughout. And then get into some benefits of AME, potential uses for AME within future XR devices, and then also relevant recent AME advances and some example applications. And then finally cover growth areas needed by AME to more fully impact high volume manufacturing of our future electronic devices. And quick caveat, I'll cover a lot of spaces within this, but of course it's very broad for additively manufactured electronics, so I'll definitely not be able to cover it comprehensively. So my apologies if I don't cover some of your favorite areas of interest. So let's go ahead and dive in. Starting by defining additively manufactured electronics, purposes of this talk, we'll define that as being the printing of conductor and then either printing of or using existing dielectric with optional additional supporting processes. So there's many different ways of creating typical features like traces and vias, either writing them or jetting them conformally onto existing dielectric structures, and then options of creating a 3D printed dielectric form, then also depositing conductive features in a more conventional flat 2D print method. Overall, additively depositing conductive materials onto either a deposit or already existing dielectric. So the most common additional process to add into the mix is pick and place, for placing and integrating in silicon and other components. With AME starting to overlap a bit with some other electronics fabrication approaches like FHE, in-mold electronics, and structural electronics, highlighting here the similarities, but overall specifying AME to be methods which leverage at least one printing technique and then while fabricating an electronic device. So selecting the appropriate AME method for an intended application requires many considerations to be made, highlighting here a decision matrix of sorts, outlining the broad conductor deposition methods as well as substrate material systems that are needed for considering to achieving a specific target function of interest. And then this all influences the overall material formulation to be used for the manufacturing process selected to make the overall AME manufacturing selection. And then on top of this, there's considerations needing to be made around the intended feature size as well as the targeted throughput, with orders of magnitude of differences in terms of the fabrication speeds and feature sizes between different AME methods. Showing here, there's a trade-off space of sorts, pushing either more on throughput or feature size, with some approaches being more conducive for high volume manufacturing and others being closer to the line and space targets for traditional electronics like PCBs. And one particular space that is compelling for AME applications I'll be referencing is that of heterogeneous integration. So this represents the current forefront of pushing electronic densification and advanced packaging, wherein multiple functionalities are fabricated together within a condensed form factor. You incorporate in embedded dies and passives, compact interconnects onto a high-density multi-layer substrate with antenna, shielding, photonics, and other functionalities all integrated into the modern heterogeneously integrated system and package. So I've overlaid on top of these places where AME is already finding uses, as well as outlining how far out in the future the use of AME within a production environment looks to be possible within this HI framework. I'm especially highlighting this as an opportunity for AME as electronics manufacturing is heading in this direction and is needed for many of the future consumer electronic devices, as well as given my involvement with organizing a framework for this in an upcoming chapter of heterogeneous integration, which I highly recommend for all those interested in understanding the directions of our future integrated electronic devices. So this brings us then to AME benefits and rationale for using AME for electronics manufacturing, highlighting in terms of the efficiency of depositing materials only where you need it compared to traditional methods which utilize aerial deposition and then selective etching, as well as the design freedom that is gained, coupled with an ability to rapid prototype for fast learning cycles, enabling ideation, design, fabrication, testing of a device within significantly shorter timescales, from cycles of days or weeks for traditional processes to hours or even minutes within some AME processes. And then also novel form factors